Okay, so in the last lecture, we covered the concept of magnetic field due to a magnetic dipole. We went over something like magnetic dipoles, and we saw that how the magnetic lines of force usually emit from North Pole and enter from South Pole, and how a ring or a circular current carrying loop acts as a magnetic dipole. Apart from that, we discussed some things about magnetic dipoles notation, that is M, and we said that it was equals to n hat nia. And apart from that, we studied an expression uh, in which we transformed the expression of magnetic field intensity in terms of a magnetic dipole, in terms of magnetic dipole M. After that, we just pointed out a fact that if the point at which we are measuring the magnetic field is not on the axis of that circular loop, what will be the expression, or what will be the expression that is derived for magnetic field intensity in that case by using spherical coordinate systems. And I told you that that thing corresponds to the example that we did in the last assignment. Now, the topic for today is basically a magnetic force between two parallel conductors. Now, let's talk a little bit about that. We have been studying about the magnetic force, we have been studying about the current, we have been studying about the magnetic field intensity H that was generated as a result of a current that is passing through a straight conductor or a circular loop or some things like that. And we studied that how if such a conductor which is carrying a current, it is placed in the vicinity of an external magnetic field, how that magnetic field exerts a force on such a conductor or such a loop or any structure or any length carrying current for that matter. But there is another thing. We know that whenever a current passes through a conductor, we know that that passage of current through that conductor that results in an a magnetic field of its own. For example, we were talking about calculating the value of force when a conductor, a current carrying conductor, was placed in any external magnetic field corresponding to the topic that we discussed at the start of this chapter. We said that there will be a force, and we figured out the direction of that force. But what if the conductor that is carrying current, it also generates a magnetic field of its own? It means that if we have two conductors, or if we have more than two conductors that are placed in the vicinity of one another, and both of them are carrying currents, that means that there is one magnetic field that is being generated due to conductor 1, and there will be another magnetic field that is being generated due to conductor 2. It means that these two magnetic fields will interact with each other, and as a result there will be some kind of force that will act on conductor 2 due to presence of magnetic field uh, due to conductor 1, and similarly vice versa, the conductor 2 will also experience some kind of force due to the magnetic field that was generated by conductor 1. So let's talk a little bit about that. uh, in order to understand this concept, he is saying that let's suppose we have these axes. Let's draw uh, some axes. Okay, he's saying that we have two conductors and they have infinite length. Like we have one conductor that is placed over here. We'll try to draw that conductor as straight as possible. So this is one conductor, and then we have another conductor which is placed over here. Okay. and he's saying that the distance between these two conductors is d. So if we depict this distance with a variable, we'll say that it is d. So if it is d, then this side will be d by 2 and this one will also be d by 2. Another thing that he is giving us is that the amount of current that is flowing through this conductor, or the direction of current that is flowing through this conductor, is this in the direction of z. So we'll say that this is conductor 1, this is conductor 2. So the current passing through this conductor is I1 and the current passing through this conductor is I2. Apart from that, he's saying that if okay, due to the passage of this current, there will be a magnetic field that will be produced by this conductor. We'll say, or will denote that magnetic field by the notation B1, and will denote the magnetic field generated by second conductor to be B2. So he's saying that the current passing through this is I1, I2, B1, B2, and I think this is it for now. This is y-axis, this is z-axis, and this is x-axis, as we have already studied. So yes, if two of them are placed near each other, both will exert a force on each other. Let's consider two very long conductors like we did here. Now what we are trying to do is that we're trying to estimate the magnetic field that is being generated by this conductor. Why? Because we want to calculate the amount of force that this B1 will exert on this conductor, conductor 2. Similarly, we'll find the value of B2 and then we'll calculate the value of force that is being exerted onto this conductor by this magnetic field. So first of all, we will try to find the value of B. If we reflect back to the last lecture, we know that the value of B due to a current carrying conductor, that has to be mu naught I over 2 pi r. We have derived this equation. So we need to apply this equation in for this case. If we need to apply this equation for this case, we know that the current flowing through through conductor 1 is I1. The distance or that is between these two things, this is d, and apart from that, we need to mention this phi for this case also. Now how do we mention phi for this case, or how do we know that the value of this r is d? For that, we need to know that how can a magnetic field that is generated by this conductor can interact with this one. We know that the magnetic field is usually in the form of concentric circles around the conductor. So this field line is not interacting with this. There is another one, there is another one. So the maximum uh, or the minimum line that will interact with this conductor will be something like this. So I'll have to draw a pretty big circle. I don't think I have enough space for that, but I think you get the idea that we're talking about a circle which has this conductor in the center of it, and this is basically those lines of forces, the minimum lines of forces that starts acting on, yeah, starts interacting with this conductor. So this is basically B1, and what will be the direction of B1? We'll use right hand rule for that. If we place our thumb in the direction of current, our fingers will tell us what is the direction of this B1. So if our thumb is in the direction of I1, we know that the direction of B1 should be something like this. Okay, so we have this thing. Now this phi, because we want to know what is the value of B1 at this point, so we'll need to express this phi for this point. At this point, we know that if we want to calculate, if we want to represent the direction of B at this point, it will be uh, tangent to this point. So it will be in minus x direction. because it is going to be into the screen. So we can say that phi hat here is going to be minus x hat, and this radius is going to be d. So that is why we're changing or replacing r with d. So now what we're going to do is we're going to write the value of b1. B1 is equals to minus x hat mu naught I1 over 2 pi and d. So we have the value of b1 now. What do we need to calculate? We need to calculate the force that is acting on this conductor due to this magnetic field. So we need to calculate the value of F2. Reflecting back to the last lecture, or 2 lectures back, F was equals to I into L cross B. Okay, so this is F2 we're talking about. So F2 is equals to I2 into what is the length of this conductor, although it is infinite, but we will mention it by small l, and direction of this length obviously will be in the direction of current itself. So z hat L cross B1. Now there is a possibility that there is a question in your head that why are we taking this b1 to be this b to be b1, why aren't we taking b2? That's because if you reflect back to the simplest case, when we calculated the values of forces, we know that the current this force was acting on the conductor on which we were doing our analysis on, and the current was also through this conductor. So if this is the conductor we want to find the force acting on, so F2, we will use the current which is on flowing through this conductor, so I2. We will use the length of this conductor, so L, but we were using the value of B that was externally applied in that case, in the simplest case. So we have to use the value of b1. This is being applied externally. We're not talking about the magnetic field of this conductor itself that will have an effect on this conductor, not on its own. So uh, yeah, this is b1 vector. I2 z hat L cross b1 was minus x hat mu naught I1 over 2 pi and d. So z hat cross minus x hat, that will give us minus y hat mu naught I1 I2 length over 2 pi and d. So this is the value of F2. This is the value of force that is acting on second conductor due to the magnetic field that was generated by the first conductor. So this is F2. If we want to calculate the value of F1, we are going to adopt the same uh, method. For that, we will have to find the value of B2. What will be the value of B2? So if this is the circle like we did draw for conductor 1, and this is D once again. So what's the direction of this circle? Thumb here, this will be the direction of this circle. Okay, so at this point, what is the direction of B? B is coming out of the screen. So in this case, the phi hat is equals to x hat, and apart from that, we'll have mu naught, we'll have I2 divided by 2 pi d, and we'll put this into this equation. F1 is equals to I1 into z hat L cross B1. Once again, I1 z hat L cross mu naught I2 divided by 2 pi d, and the value will come out to be y hat and mu naught I1 I2 small l over 2 pi d. This is the value of F1. This is the value of force that is acting on conductor 1 due to the magnetic field which was generated by conductor 2. So we have the value of F1, we have the value of F2. If we want to mention these forces graphically, what is the direction of F1? It is in the direction of y. Okay, so the force acting on F1 is in the direction of y. This is the direction of F1, and the force acting on F2 is in the direction of minus y. So this is the direction of F2, which means that if these two conductors are placed like this, they will experience a force of attraction. You can see from this graphical representation here. So they will experience a force of attraction, and if the direction of current in one of them is reversed, as a result, these two forces or these two conductors will start to repel each other, because in that case we will have minus z here, and once again we'll have minus here, and these two forces will be equal, and these two forces will be in opposite direction, so they will repel each other. So if the direction in the two conductors is same, the force will be the force of attraction, and if the direction in both conductors is opposite, as a result, the force that is being applied due to the magnetic fields of both these conductors and the interaction of their magnetic fields with each other, that is going to be repulsive force. So yeah, there is that. He has also mentioned this force in the terms of force per unit length, like F2 dash. That is going to be F2 divided by small l, and that is going to be minus y hat mu naught I1 I2 divided by 2 pi d. This is per unit length. And similarly, you can write this for F1 dash also. That is going to be y hat mu naught I1 I2 divided by 2 pi and d. So this is how we are going to find the amount of force that is acting on one conductor due to the passage of current from another conductor. Okay, the next topic of our discussion is going to be Gauss's law. Gauss's law for magnetic field. Okay. So why are we studying Gauss's law here? I told you that we'll have a counterpart for everything that we have studied in electrostatics here in magnetostatics too. So what was the Gauss's law? The Gauss's law for electricity was basically nebula dot d, and we said that it was equals to rho v, or by using divergence theorem we transformed this into this form, d dot ds, this is equals to q. And if we want to express Gauss's law in terms of yeah, in what do we say, in words, that is going to be the net outward flux of d through a closed surface is going to be equal to the charge that is enclosed by that surface. This is basically Gauss's law. So we will compare the Gauss's law for electricity with Gauss's law for magnetism. So we have changed the Gauss's law from this form to this form by using divergence theorem. We have already studied this. Apart from that, we also had another form of Gauss's law in which we changed this uh, q into volumetric integral and then rho v and dv. So we'll compare these things with magnetism. If we compare and we try to find out the magnetic analogs or magnetic counterparts of all these things that are being considered in this law, he's saying that magnetic analog to a point, what is the magnetic analog to a point charge? What is the magnetic counterpart of a point charge? He's saying that counterpart or magnetic analog to a point charge is basically magnetic pole. So magnetic pole is the counterpart of point charge in magnetostatics. He's saying that we have already talked about this, but we'll talk about this here in a little bit more detail. He's saying that an isolated charge or a point charge can exist in isolation, but we have already seen or we have already witnessed that a magnetic pole cannot survive in isolation, or it cannot exist in isolation. It will always be in pairs. We have seen an example of this by talking about a bar magnet, and we talked about the experience that we had in our childhoods, that if we even if we break that bar magnet into two pieces or into three pieces or into four pieces for that matter, we keep on breaking that magnet into small and small pieces. Every piece is going to have a north and south pole of its own. There is no way that if we break a bar magnet from yeah, in the middle, we'll say that we have a north pole that is isolated now, and we have a south pole which is isolated now. Both of those pieces are going to have the north and south poles. So we derived the conclusion that the magnetic lines of force are always going to be in the form of closed loops. That means that magnetic lines of force are not being generated or terminated anywhere. They are in the form of continuous loops. Why are we talking about loops in Gauss's law? Because we need to talk about uh, loops, because when we discuss about Gauss's law, we know that we basically enclose the charge that is present on a surface, or a point charge, or or a volumetric charge density for that matter. We enclose that charge into a imaginary surface, a Gaussian surface, and we measure the amount of uh, magnetic or electric lines of force that cross that surface. We basically sum up all those lines, that d dot ds, we sum up all those lines, and we'll say that this is equals to the amount of charge that is enclosed in that surface. So we'll reflect back to the example of point charge, like how did we calculate the value of electric field due to a point charge by imagining a sphere around that. But he's saying that if we apply the similar, or if we implement the similar concept to a magnetic field, that is not going to work. Why is that? It will not work because if we had a positive charge and we imagined a sphere around it, there was there were a lot of electric lines of force that were emitting from this charge, and we calculated the value of d dot ds for this whole closed surface. As a result, we had some kind of value, and we said that that value was equals to the charge enclosed. But what if we have a magnetic uh, thing, or a bar magnet for example, and we want to apply the same scenario to this thing too? So what we did was we imagined a sphere, and we imagined that this magnet was uh, present inside that sphere, or that sphere has enclosed that this bar magnet in itself. So what's going to happen is that uh, there will be some kind of lines that will emit from north pole, and they're going back, and they're re-entering from south pole. So as we know that these lines are always going to be in the form of closed loop, it means that whatever line will leave this surface will come back through this surface from opposite direction. So it means that if we take an integral of this whole closed surface, if we take an integral of this whole closed surface, the number of lines that are leaving this surface will be equals to the number of lines that are entering this surface. What will happen if this is the case? What happens is that integral of this thing is going to be equal to 0 always, because there will always be whenever there will be some lines that cross that surface or go out of that surface, there will always be the same lines that are re-entering that surface, and because that surface is completely enclosing that bar magnet, it means that it has to go through that surface. So this B dot ds will always be 0. It means that we have transformed the Gauss's law for electricity into the Gauss's law for magnetism. So for this case, we'll say that nebula dot B will always be equals to 0, or by using divergence theorem, we can say that B dot ds is always going to be equal to 0. He's saying that the charge can exist in isolation, but a pole can't. If we had a possibility of having a magnetic monopole, then this will never be this won't be equal to 0, because we'll have a north pole here, and we could have imagined a sphere around it, and it will only emit the lines of force, and there would have been some value of B dot ds in this case. But that was only possible if we had a monopole, yeah, if a monopole pole's existence was possible. So we'll say that this is not possible. So if this is not possible, and it is always going to be uh, two poles whenever we will talk about a magnet, so he's saying that that means there is no equivalence to a charge q or charge density rho v in magnetostatics. There is no way that there's going to be some kind of charge distribution on anything, or there's going to be some kind of magnetic monopole that could exist. So that is why we'll say that this is the Gauss's law for magnetism. And this thing is also known by two others names. We'll say that one other name for it is a law of existence non-existence of law of non-existence of magnetic monopoles, because this is the conclusion that can be drawn from these two equations directly. And the other name for this is law of conservation of magnetic flux. Law of conservation of magnetic flux. So these are the two other names for Gauss's law of magnetism. Okay, so he's saying that a difference can also be viewed in the form of field lines, like we have talked earlier. Electric field lines originate from positive terminal and terminate in the negative terminal. So electric field through a closed surface, that is not going to be zero in case of in case of electricity. But in contrast, when we talk about magnetic field lines, they will always form continuous loops. So it means that whichever line will exit a closed surface, it has to come back, because it has to complete its closed loop, and as a result, the integral of all those lines that are crossing that surface, that has to be 0. So this is it for today. We'll talk about Ampere's law in the next lecture, and that Ampere's law uh, is going to have the importance that Gauss's law had in electrostatics. Like we used Gauss's law to find out the value of electric field intensity, but like we have studied here, Gauss's law of magnetic field is not going to help us much if we want to calculate the value of magnetic field intensity. So it means that we have that space, that space that was required to find out the value of H more easily as compared to Biot-Savart law. That space is still empty. That space is going to be filled by Ampere's law. Ampere's law is going to be that tool which will enable us to find the value of electromagnetic field intensity more easily as compared to Biot-Savart law. So in that way, we can say that uh, the Ampere's law will perform its function like the Gauss's law performed its function in calculation of electric field intensity in electrostatics. So we'll talk about that in the next lecture. This is it for today. If you have any questions, you are welcome to ask them in the interactive session. Thank you so much.